there's so much money that it kind of warps everything, that you think, oh, it's too expensive, but actually it's not too expensive. We are primarily optimization and simulation tool for thermofluids. What matters is that from the 1st to the 50th to the 25th time, it's getting better, and those design cycles are really short. But once you take a step back, look at the problems, really understand what people are trying to solve, turns out it's physics is physics, and it's the same no matter what industry you're in. I think in the next 3 years, the most successful AI tool engineering is going to be AI agents. I'm a believer. Let's put it that way.
All right, Thomas. Thanks so much for doing this.
Thank you so much for having me.
Really cool. Today we'll talk about generative design and topology optimization in engineering. But before we get started, Thomas, what are you actually doing at Toffee?
What, me personally?
Yes.
So me personally, I obviously, with a small company, you have to do a lot of different things. But I'd say the majority of my time right now is I work primarily in partnership building, especially sort of open innovation. So attracting investments in terms of like grant funding from both other industries, other companies, and also from public grant sources. And I'd say that's probably about 50% of my time. And then because of my sort of work in that, I also have some idea of how to direct the R&D that's happening here, just using our internal funds here at ToffeeX. But yeah, like I said, there's many other things that I do in my day-to-day. Work a little bit in product. I work a little bit in doing the actual development itself, right? Getting my hands dirty on the code, working with our academic partners and so on. So a little bit of everything, but mainly sort of like understanding R&D and how we can best apply sort of R&D resources here at ToffeeX.
Super cool. Yeah, that's the beauty of working in a startup, right?
It's my favorite thing about working on a startup is being able to do loads of different things and needing to do those different things, in fact.
Yeah, it's pretty cool. What is Toffee doing in the first place? Some people say it's kind of a generative design software. Some people say it's fluid topology optimization, whatever that means. So what do you actually do?
It can be all of the above. So I think basically, if I were to pitch Toffee, first time to someone who's never heard of us, I would say that we are primarily an optimization and simulation tool for thermofluids, right? So it's quite specialized. It's quite niche. We're not going to be able to solve all of your engineering problems, but if you have a thermal management or a thermofluids problem, then I think we are an essential part of the design process for that. It's a slightly different tool from what people are used to working with, and that's absolutely correct. It's new. It doesn't quite fit into any sort of different. It doesn't really fit into a specific bucket, but it is an optimization and design tool for thermofluids.
Got it. When we talk about some application, Thomas, what I would think about first when I hear this is heat sinks. Is there anything else that people can imagine when they think about Toffee?
Yeah, absolutely. So basically, it's let your imagination run wild. Heat sinks obviously is very important part of our business. So both actively and passively cooled heat sinks. But really things like cooling plates, both on small scale, so for like small inverter or power electronics, or large scale, so things for like battery packs in electric vehicles, heat exchangers, two fluid heat exchangers, air, oil, fuel oil, air, fuel heat exchangers for energy and aerospace primarily. Manifolding problems is another big thing we do from in automotive and aerospace, where it's fuel delivery or exhaust manifolds, or even we work also now more and more in things like manufacturing. So injection runners for like high pressure die casting is a manifolding problem. It's a fluids problem, and that's something we work on as well. So it's any sort of internal fluid dynamics or thermofluids problem. We've managed to find some success in almost everything we've worked in.
Yeah. When we think about the heatsink, I think it's probably the easiest example for people who are listening to this podcast. How does the interplay work between, let's say, the generative part, the generative design part, and the topology optimization part, as well as the CFD bit of it?
Okay, so maybe we start answering that question with some definitions then. Yeah. All right. So I think we start at the most the most basic, which is, CFD is quite ubiquitous now as a tool in terms of reducing cost of development for engineering problems. It's much cheaper to run computational simulations now for fluids than to buy some time in a wind tunnel. And CFD is really the basis of what we do, right? So underlying almost everything we do at ToffeeX, there's a CFD simulation. On top of that CFD simulation, we have a topology optimization tool. So what is topology optimization? So topology optimization, it's I guess you can describe it as an algorithm, but like it's a mathematical process, optimization process, which allows users to create optimal designs for something that obey certain rules of physics. So if you imagine in our context, we want to create an optimal design for a heatsink, right? And there's certain requirements for what is optimality in a heatsink. So the classic examples we use in all our communications is you want to minimize the pressure loss of the fan blowing the air across the heatsink, and you also want to minimize the temperature of the thing you're cooling. So you can write this mathematically. You can write, minimize my pressure plus temperature. But that doesn't tell you anything about what you are allowed to do with the pressure and temperature, right? It's very easy if you want to minimize it. You say pressure equals minus infinity and temperature equals minus infinity. But, this is obviously nonsense. So you need to give some more information to the optimizer to say, minimize my pressure and temperature, but also you need to follow these rules. And so in our case, and in topology optimization, the rules are the physics equations and the fields given as solutions, but these physics equations, which we calculate with CFD, obviously. But if in more conventional topology optimization for things like structural problems, they solve linear elasticity with finite element solvers. And so, that's like the really high level sort of basic description of topology optimization. It's an algorithm. It allows you to optimize with certain constraints which represent physics. At the top level, then, you mentioned generative design. So generative design is more of a, maybe it's more accurate to describe it as a philosophy or something like this, right? There's no one generative design. Mm-hmm. And if you ask different people in different industries, it will mean slightly different things. But I think probably the most uncontroversial way of describing generative design is that it's a design process where there is a computational algorithm generating designs based on inputs from a user. So there's like this process where a user defines inputs and selects an algorithm. And then the algorithm takes these inputs and runs and generates loads and loads and loads of designs, right? And then at the end, you have loads of designs, and then it's back to the engineer or the architect or, the industrial designer, whoever's using the generative design tool, to use their own, expertise and, experience to dig into all of this messy data, some of which may be nonsense and some of which you hope is really high quality stuff, to go through there and choose the best ones and then develop them further. That's basically, I think, the three definitions here. So you can see we fit into almost all three of them, right? We're generative design because we generate designs using our topology optimization algorithm. Mm-hmm. And our topology optimization algorithm sits on a CFD solver. I say we're a generative design tool, and we're also topology optimization. So we have the paradigm of generative design, and that's the way to get the most value out of our tool. But really, the concrete thing we're doing, it's topology optimization or fluid topology optimization, really. Yeah. So I think that's probably the easiest way of thinking about this.
Yeah, that makes sense. I think what I like, what you mentioned, Thomas, is that the theory itself is relatively straightforward, quote unquote, right? I mean, the Navier-Stokes equation is maybe not that straightforward, but at least the heat transfer equations, this is pretty straightforward from a physics standpoint. The question is, where is the secret sauce? Because there's obviously some competitors in the market that claim to be better than ToffeeX, but obviously there has to be something that you guys do better than the rest.
Okay, so that's a great question. And like you said, I think it's the concepts are really quite simple to grasp, I think. And it gets messy, as with all things, once you dig into the details. But to answer your question, I think there's two distinguishing features. So the first is basically compromises you make in your algorithm, in like the core logic of what you're doing with the computer. Because I mean, and they're engineering compromises, right? And everyone makes engineering compromises, right? Whether you're making an airplane or like an electric toothbrush or software, at some point you make an engineering compromise, and really it's your decisions on those engineering compromises that allow you to win or lose in a market, right? Like you know, if you look at just maybe a dumb example, you could say, oh, I want to design like a mass market car and I want it to cost less than 20 grand and it needs to have all these things. Well, there's loads of cars available for 20 grand, but each of them have made different compromises on what is acceptable. And then in the end, someone wins because they have chosen the one that's most acceptable to the market. And it's the same for us, right? Like, so there's decisions we need to make on like, what types of physics are we going to model? Like, how accurate do we need to model the turbulence, right? What types of geometries do we allow in our generative design? Like, what kind of applications are we targeting? What are we tailoring our things to? And I think this is one aspect of it, of what differentiates us in the market against competitors. And there's also other things here, just in terms of like speed of the algorithm and so on. How much do we use AI acceleration or machine learning or data-driven approaches, and so on. So I think that's one side. And I think basically our view of this, like the decisions we've made, is just to be super ambitious and dedicated to our core tools, which is topology optimization, right? So we don't have any like add-on implicit modeling or, latticing or whatever it is. Like we do TO, like, and that's what we do. And everything we do, it's a variation on the TO. And I think that's kind of like what really sets us apart in the market. But there's a second thing, which I think is more of a strategic decision, which is, there's a lot of new generative design tools available, more and more and more in the market, especially for engineering. And when you're trying to sell these into a particular industry, it's difficult because people have their processes. They know what they know. They know what they like. They know how it works. And now there are these ragtag bunch of 25 people in an office in London who come up to you and be like, hey, I've got something really cool, right? And the question you have to answer then that we have to answer as ToffeeX is like, what in the process, what in the design cycle, what in the experience of using ToffeeX is going to fit into our customer's design cycle, right? And this sort of leads to making decisions on like, what is the experience like? And for us, the decision we came down to is like, the most important thing in the experience is being able to iterate rapidly. And it doesn't matter if you don't get things right first time. It doesn't matter if you don't get things right on the 15th time. What matters is that from the 1st to the 15th to the 25th time, it's getting better. And those design cycles are really short, right? And so this is a very specific way of thinking. Okay, I don't know what everyone is doing, but I certainly think we're probably one of the most advanced in creating a tool that's built around that way of thinking. And I think this is our other kind of like distinguishing features, like the speed of iteration which we enable is probably, I don't think, I'm not going to say we're the best, but we're pretty far up there, I'd say.
Yeah, definitely. Before we talk about kind of the integration into the engineering ecosystem, I would like to talk to you maybe one last thing about generative design, CFD, and then we have topology optimization, right? Mm-hmm. 3 topics, 3 very complicated topics. It seems very easy to grasp when you have these subjects in uni, right? The question is, how do you divide and conquer such a problem? Let's say someone comes with a heatsink, they have different criteria to fulfill. How do you tackle such a problem?
It's hard. It's very hard. I think it's I think my view personally is that nothing is really an island, in the sense that the connections between different industries are far more than you think, right? So and this is something that's sort of borne out by our experience, is that we've developed tools for application whatever. So some let me think of an example here. There's heating tools where when you have some object that's generating a temperature, it's generating heat, and you're trying to cool it, and you're trying to like conduct the heat out of the source into some heat sink and then out into the atmosphere. And this sounds very specific, right? Like the combination of fluids and thermal management and the conduction in the solid and all the rest of it is like kind of very specific. But if you just remain within thermal management, it's still the same problem. Like whether you're doing this or you're trying to make sort of like some sort of turbulator for a cooling channel, or maybe like a two-fluid heat exchanger, slightly different, but we can reuse a lot of our fundamental sort of like algorithms there. But what we've learned also is that these equations that we're solving, they're not miles away from things that seem radical. So like we've done some work on it's one of these things I can't say too much about, but like it was basically a chemical filtering process. And we'd spent like 6 weeks like hashing through equations on scraps of paper and on the whiteboard, trying to like figure out how we can take these chemical processes and port them into our optimization tool to create some sort of novel topology optimization tool. And after about 6 weeks of hashing through it, we kept on landing back at, once we've made all our simplifications and so on, the equations looked almost identical to the thermal management equations. It took us a while to accept, but after a while, when we ran the simulations, and then eventually when our customer ran the experiments and stuff, turns out they were the same, right? If you look at like classes of physics equations, in terms of like the really common ones, there's not that many, and they're all just variations on a theme. And what this means for us, and what makes our life a lot easier here, is that a lot of these things seem very separate. Once you boil it down, physics is the same, right? It's not because you're now working in a different industry that the laws of physics has changed. So all it takes is small changes, not just, and even small changes that can be just in the way it's presented to the customer, right? This customer uses these words to describe these things. This customer uses these words to describe the same things. And it's just understanding that difference, understanding that nuance, and just giving people what they need from that perspective. So yeah, it's very disparate, can be very, initially seem completely different. But once you take a step back, look at the problems, really understand what people are trying to solve, turns out physics is physics, and it's the same no matter what industry you're in.
Yeah. Give me a realistic breakdown of if a customer comes to you and they bring the geometry with them, right? How does the process of using the tool look like? That's another question I have. Yeah.
Okay. So I guess the first thing is this kind of depends on what stage of their project they're at, right? So let's say this customer comes to us very early stage, and they have an idea of what they need in terms of like, they know the space available, they know their weight budget, they know a little bit about the sort of like the operational and capital expenses that they need to budget against. But they might not yet know, how am I going to manufacture this? They might not yet know like acceptable sort of like exactly their economic model for their products. And they're just trying to explore and just figure out what can they achieve. So in this case, they come to us and we say, hey, here's the software, it costs this much, have some fun. But really what they need to come in with is basically their component requirements from their systems engineers. So it'll be like, I have this flow rate available, I have this much power I need to dissipate, this is my weight budget, and this is the space I have available. And then from that, they can do some pre-work, likely in a CAD tool, or maybe they can do some initial sort of like simulations. But at that, once they sort of really know what they're doing, they can export their design space from their CAD tool into ToffeeX. They can then set up their physics problem. So set up the CFD problem. So they need to know their boundary conditions. They'll need to know their temperatures, their powers. They'll need to know what materials they're using, what are the properties of the fluids. Basically anything you need to run a simulation, which they have. And then they set up their design exploration. So what does this mean? Is that when they'll set up an optimization problem, which is the relative importance of my different optimization goals. So the relative importance of pressure versus temperature versus heat transfer versus weight, and so on. And they'll also have a bunch of other constraints they can play with. So they might want to explore what happens if I run a completely unconstrained optimization, or if I run a optimization that's constrained to be manufactured using a cold forming process, or an optimization that's constrained to be manufactured using additive, or maybe they want to explore like a casting process and so on. But what they can do is, once they've set up their problem, it literally takes seconds to just try something new in that space. So it's just a case of, okay, I've got my problem set up, I'll duplicate it, and I'm going to see what happens if I optimize for additive instead of like a stamping process. Now I'm going to see what happens if I optimize for slightly lower mass flow rate, or what happens if I have 10% higher power that I need to dissipate, or how different is my design if I need to design for off-design conditions. All these things. And the idea is that the customer then can generate, this generative design loop where they generate loads and loads and loads of designs. They might explore their optimization front. They might explore the trade-off, right? Okay, they can design for additive. The component now is going to be much more expensive, but maybe the freedom of design you get with additive means that the performance is so much better that it's worth actually investing in additive versus sticking to like a conventional design where you get worse performance. And yeah, it's cheaper, but maybe the balance comes out ahead for additive. And so there's this whole design cycle. They'll probably generate maybe hundreds of different designs, and most of them, the engineer is going to be able to say, I have experience in this. This one's a bad idea. But out of these, they might pick out maybe 5, 6, 7, which are like the most promising. And then they can bring that back to the rest of the engineering team and say, hey, any of these look promising to you. And then they can move on with their design cycle. So that's how you could use it in an early early design process.
That makes sense.
Yeah.
I'm wondering, Thomas, from an ecosystem point of view, how easily does Toffee fit into existing processes?
Yeah, good question. This kind of like goes back to what I said earlier about like the importance of when you're a new company with a new tool and a kind of a new paradigm, you need to, it's not enough that it's easy. It's like you need to know how to do it, and there's slightly different things, right? It might not be the easiest, but if you know exactly what needs to be done, then that's still a good enough for a lot of people. The other thing I've learned, so I used to think it's important for everything to be like seamless and integration and everything's automatic and you just click a button and everything's good. And what I've learned is like, that's good. That's fine. That's nice. It's good if you have it. It's better if you have it. But it's actually far, far more important just to really do the really simple stuff. Import and export in files that are common, right? Make sure, because we're working with geometry and there's like, it's very easy to mess up geometry files. Make sure your geometry files are like high quality, good representatives of what you're trying to achieve. Make sure you're working in common formats for things like simulation meshes and field data and just these things, because for the most part, if those are all high quality and they fit the standards that people expect, engineers don't care if they have to save it and then drag and drop it into another like program. Like, that's fine. It doesn't matter. It doesn't need to be super seamless for everything. It's more just really basic stuff done to a high quality is plenty from a sort of a practical point of the integration. There is like the higher level of like, how is the best way to use this in the system? And that one is much more difficult to answer. And it's kind of, that is a case by case because, you know, every customer is a slightly different process and they work in a different industry and their regulations are different and so on. And that's something you need to tailor a little bit more to each customer and really get their input and allow them to explore and try it out and figure out for themselves what is the correct way of doing things.
Yeah. I feel like especially when you're developing software, it feels like, maybe that's a bad comparison, and excuse me for the comparison. It's more like if you develop an airplane versus a car, because with the airplane, you have like fixed rules on how the pilot is going to be educated about how to use the airplane. And for a car, software development feels more like developing a car because you might have a lot of people who don't know how to use a car or drive a car properly because there's not really one single standard of how to actually use a car. There could be a million different scenarios how people can misuse it, etc. So the question, why I'm actually saying this is, what are the end users interested in when using Toffee, and what are the C-level executives interested in when using Toffee?
I like your analogy, first of all. It was maybe a little bit strange, but I think you're absolutely right. Like, there are certain users who are highly regimented and they know exactly what they're doing. And they know exactly, if I have this problem, then I solve this. I have this problem, then I solve this. And then there's others who are like more generalists and they come in and they're like, don't really know what they're doing, but they always kind of like figure it out and so on. So to the other question, I mean, the C level is pretty easy. They want to make money. Both short term and long term, right? So whenever they see Toffee, they're looking at what does this enable, right? So with Toffee, it enables 20% shorter design cycles, or it enables us to use additive to its highest potential, or it just enables X% better performance of our products, and so on. And basic fundamental is all really just tied to, we need to make the best product we can, right? And that's, this is normal. This is their job. The engineers, on the other hand, they're more of a mixed bag, I feel, when I'm interacting with them, because there's, we get different, you get different archetypes, different customer profiles, right?
That's exactly what I mean. That's exactly what I mean, Thomas, because the thing is, if you do a normal driving license, you could have one car that's the perfect car, but then if the driver is in the wrong seat, it doesn't matter if the car is great.
Yeah,
exactly.
Yeah, but I mean, this is a difficult thing for us, right? Because we're such a new tool. It's not like, oh, we've got like this new CFD tool, we got this great new CFD algorithm, like it's Lattice Boltzmann, but like times 3. When you go to a company with that, they're like, okay, I know who you need to speak to. It's this team over here, right there, the CFD experts. We're going to go, and then when you speak to them, you're speaking a shared language.
Yeah.
Or if you have like a new CAM tool, or like I've got this build prep tool for additive, and so it's got all these crazy new features, AI, whatever, X, Y, Z. They're like, okay, here's the additive team, right? Go speak to the additive manufacturing team. They know exactly what you're doing, and you're speaking the same language. And we're turning out, and we have this thing which is like simulation and optimization and manufacturing and all of these things all together, and we turn up and we say, this is really cool, you want to try it? And they say, yes, this is really cool, we want to try it. And then you have people from CFD, and you have people from additive, and you have people from product, and you have the C-suite, and you have people from like computing coming in, and they're all interested, but they all have a different worldview, and it's a difficult conversation to have, because you can imagine also for like our training users and stuff, right? So if you're making a CFD tool, you create like the user guide for the CFD expert. But now you can imagine if you have a tool and you need to make a user guide which teaches someone how to use it, but you have someone with a background in additive, someone with a background in CFD, someone with a background in like computing or whatever it is. Now the languages you use is slightly more challenging. Anyway, how do we solve this problem? So I'm not saying we've solved this problem, but what we try to do really is to basically have different levels available in the software. So in terms of complexity, so high level, you log into ToffeeX and like it is I'm not sure if I'm allowed to say this, but like it is slick, right? There's the number of options available to you maybe is more than, actually that's not true. It's probably like less than Microsoft Word, right? Like it's really simple in terms of like you start at the top, you go through all the options. Once everything is, green, then you press go and then you go. And it's not asking you crazy questions about numerical discretization or turbulence models or like whatever. It is just like, what's the flow rate? What's the temperature? What material are you using, right? Really basic stuff that any engineer can understand. And this is great, like if you've got some generalist engineer working on, but then like the CFD expert comes in and they're like, okay, I want to know what discretization, I want to know what turbulence model, I want to, know how many iterations of this algorithm you're using when you invert this matrix, blah, blah, blah. And I understand why they know that, because they've seen what can go wrong if you don't get that right, and people should be able to see that, right? That should be available to them. But if you make it available to everyone, the poor old additive manufacturing engineer is going to be looking at this option and kind of freaking out. But if you sort of like, if you understand that, like you start from the basics, right? The basics that almost anyone can use. And then as people ask for more and more things, you can give that to them as an option. And if they want to, they can go into it, but they don't have to. And just building this up in layers sort of allows you to solve most problems. Not all. Some, this is, we're not there yet. But it has, let's say, compared to where we were like 3 years ago, this understanding has like really reduced our pain.
Yeah. I feel like one thing going back to the beginning of the conversation, Thomas, what I really liked is that you don't do this kind of implicit modeling thing. You really focus on what you do best, because I feel like a lot of software companies or SaaS companies, they're focusing a lot, they're falling into this feature paralysis, so to speak. So they want to build more features, and then they think that this one feature is going to change everything, which is not true.
No, absolutely. Yeah, this is something I feel really strongly about, actually. Like if you want to be successful, and this applies not just like if you're starting a company, this is just like anything anyone does ever. If you want to be successful, you need focus.
Yeah.
You cannot be distracted by the shiny thing. Like you need to identify what you want to do and commit to it. And frankly, 9 times out of 10, it's not going to work, right? 9 times out of 10, you'll have committed to the wrong thing. But that 1 time out of 10, you will be successful. But if you start getting distracted by this and that and the shiny thing, whatever, like it's never gonna work. Yeah. And so having that focus and that faith that what we're doing, we believe in it and we're going to do it, and everything we're going to do is built around this. It's not sufficient to be successful, but it is necessary.
Mm-hmm. Yeah.
And it drives focus and it drives work. And also, I think also it's, and this is a personal thing, but for me, it brings more satisfaction, right? Like if you're doing many small things poorly versus doing one thing really well, right? I think on a personal level, but for me, that's very important.
Absolutely, yeah. Maybe one last question before we wrap it up, Thomas, is looking into the future, what can we expect from Toffee? Of course, not spoiling too much.
So I think that there's a couple of things we're working on. We've got one we're basically, okay, so let's try again. There's a couple of things I'm working on. A lot is just building on success we've already had. So we started out in aerospace. We came out of the Department of Aeronautics at Imperial College. And we've got a lot of exciting projects in aerospace right now. I'm really, really looking forward to sharing the outcomes from those. And so we'll see. Maybe some things will be built, maybe some things will fly as well. So, I mean, that would be, incredible. But beyond that, in terms of like new features, exploring, expanding new markets and so on, it's more of the same in the sense that, like we just talked about, like we want to be the topology optimization tool, right? So we're looking and developing topology optimization tools. And it's just the novelty of applying these algorithms and these tools to new, both new problems in terms of like the types of physics that we're attacking. So we were doing a bunch of projects right now on trying to do topology optimization for evaporating and condensing flows. Now, this you can I'll let people do their own research on how difficult that might be. But that's something we're really, really excited about. But also things like coupling thermal, fluid, structural systems together into like one sort of mega tool. And then applying these to completely new fields. Like I said, we've just started working in manufacturing, right? Can we optimize things like dyes and molds and so on, right? And sort of something which is completely new to us. Or even working in industries like everyone's doing it now, but it's a really big industry, which is cooling data centers, and the challenges that are there. Because it's actually, I find it a really unintuitive place to work in, is kind of like the data center world, because there's so much money that it kind of warps everything, that you think, oh, it's too expensive, but actually it's not too expensive, and it sort of changes your incentives a little bit. But it's also it's new and exciting, and we're learning a lot.
Yeah. What about AI agents? Because people say that 2025 is the year of the agents. Are you doing anything with agents and LLM to gen design, whatever?
Watch this space. Yeah, this is great. I could like talk for another half an hour about AI agents. Actually, I think just like my 3-sentence summary is that I think in the next 3 years, the most successful AI tool engineering is going to be AI agents, and it's not going to be simulation. Is it not really simulation if it's AI prediction of simulation results and so on, or whatever it is? I think AI agents in engineering is like, I'm a believer. Let's put it that way. Yeah.
Okay.
I think it's.
Maybe we can even have a demo. I'm not sure how much AI you're actually using inside of Toffee, but maybe we can have a deep dive session on kind of showcasing what's possible with Toffee. In the next months.
I'd love to. Yeah, we can maybe pull together a couple of new things we've been doing, and tie it all together. Yeah,
good stuff.
Definitely.
I really enjoyed the session, Thomas. Thank you so much.
Thanks so much, Jousef. Thank you.